Hello there and welcome to Module 5, Fundamentals of TCP/IP. This is where we start to get into real depth, nitty-gritty if you like, of TCP/IP, and the course now starts to accelerate. Modules 1 to 4 were pretty much an introduction, but now pressing on, we're going to be motoring ahead, so to speak. So without further ado, let's move on to the objectives for this module. Okay, so as you can see on the screen now, we'll go through this module. By the end of this module, you should be able to understand how the TCP/IP protocol suite relates to the OSI 7-layer reference model. Also understand the functions of the IP, or Internet Protocol. You should be able to describe the operation of ARP, or Address Resolution Protocol, and also describe the role of ICMP protocol. And obviously TCP and UDP, very important. And after this module, we should be able to describe the operation of TCP and UDP. And also you should be able to describe the purpose of telnet, SSH, TFTP, DHCP and DNS. And finally, also, you should understand the role of port numbers in TCP/IP. So before we press on, just to give you an introduction of TCP/IP. So basically, the term TCP/IP is used to describe a collection of open, non-proprietary networking standards published by the Internet Society in documents called RFCs, or Requests for Comments. The acronym TCP stands for Transmission Control Protocol, and IP stands for Internet Protocol. These are two core protocols of the TCP/IP standards. We'll start this module with a brief review of TCP/IP, its history, standards and governing bodies. This is mainly background material, however you should be aware of the main functions of ICANN and IETF, and understand the role of RFCs as standard documents. The TCP/IP protocol suite uses a 4-layer model, and you'll see how this is mapped to the OSI 7-layer model. We will look at each of these 4 layers in turn, starting from the bottom, and describe the key protocols at each layer. These protocols are covered in more depth than you will be questioned on directly in the exam. You will not be asked to describe the detailed operation of a protocol such as ARP, or to itemize the contents of the header of an IPv4 packet. However, you will need a good understanding of the protocols described in this module in order to be an effective network administrator and to answer questions in the exam, particularly those relating to troubleshooting. After a brief description of the network interface layer, we look at the Internet layer, which is concerned with IP addressing and routing. Both of these topics are covered in detail in Module 6, named IPv4, Addressing and Routing. In this module, you'll learn about the underlying core of protocols at this layer, IP, ARP and ICMP, and how they are used to enable the transfer of data across networks and to troubleshoot network problems. Moving up to the next layer, you will learn about TCP/IP and UDP, the two transport layer protocols. The detailed descriptions of TCP/IP connection establishment and termination, as well as acknowledgements and retransmissions, are included to help you achieve an understanding of and obtain an understanding of these processes. At this layer, you should aim for a broad understanding rather than concentrating on the details. Right at the top is the application layer. We describe only those protocols that are relevant to those aspects of the configuration and management of routers and switches covered by this course. These are telnet, SSH, TFTP, DHCP and DNS. However, an important concept at this layer is that of port number, which is used to identify applications. You should make sure that you know the ranges of port numbers, well known, vendor and dynamic. You will also need to know the port numbers and associated transport protocols, TCP or UDP, of a number of well-known applications, not just the ones detailed earlier. These are listed in these modules later on. Throughout this module there are references to RFCs, the documents defining the TCP/IP standards. These are given so that you can look up extra information about the protocols if you wish. You will not be expected to know these RFCs for the CCNA exam. One final thing before we press on is regarding IPv4 and IPv6. Basically all of the information regarding IP in this module and the next relates to IPv4, as does most of the material in this course. Some of the protocols covered in this module, such as TCP, will work with IPv6 as much as they do with IPv4, but others do not. For example, ARP is not used at all by IPv6, whilst DHCP is replaced by DHCPv6. Most end-user networks still use IPv4 predominantly, and IPv4 remains the focus of the CCNA exam. However, IPv6, which is covered separately in Module 17, labelled Introduction to IPv6, will become increasingly important over the next few years. So, as I've already mentioned, TCP/IP is a set of open networking standards defined by the Internet Society, or ISOC, which is a professional membership organisation. Some milestones in the development of TCP/IP are listed on the screen right now. The Internet, a worldwide network based on TCP/IP protocols, had its origin in a collaboration between the US military and academic institutions, the purpose of which was to develop a resilient network capable of functioning even when partially disrupted. The military and public implementations were separated in 1983. The Internet Society, or ISOC. The Internet Society was set up in 1992 with overall responsibility for the Internet technologies and applications. It oversees a number of subsidiary bodies, so one of which are the Internet Architecture Board, or IAB, and these guys are they're the technical advisory group of ISOC, responsible for setting Internet standards, publishing the request for comments that I touched on earlier, and also overseeing the standards process. It coordinates the efforts of the wider Internet community in developing open standards. Next, covered by ISOC are IETF, or the Internet Engineering Task Force. This group of people are responsible for developing solutions to technical problems and developing standards and protocols. Another group of people are the Internet Research Task Force, or IRTF, on the left hand side there. This group coordinates all TCP/IP research projects. And finally we've got ICANN. This is a not-for-profit organisation created in 1998, which has responsibility for the assignment, registration and management of IP addresses, protocol numbers, port numbers, domain names, etc. It took over these functions from the Internet Assigned Number Authority, or IANA, which used to be part of ISOC, reporting to the IAB. IANA now has become part of ICANN. The standards for TCP/IP are published as RFCs, which are proposed and reviewed by the community of Internet users before they become standards. Most of the standard protocols on the Internet began as RFCs. They are considered public domain documents and, with a few exceptions, are available online from several repositories. RFCs are numbered sequentially. Once given a number, they are never revised. New RFCs are issued instead. There are several requirement classifications of RFCs shown on the screen now. These determine how widely, if at all, an RFC is used. The standards track of RFCs includes 3 maturity levels, as shown here on the screen. Alternatively, RFCs may be informational, historical, or experimental. So now we're going to move on to TCP/IP protocols. Okay, so the TCP/IP protocols form part of a 4-layer architecture. By comparing the TCP/IP architecture to the OSI 7-layer model on screen, you can see that TCP/IP network interface layer, also known as the link layer, comprises of the physical and data link layers of the OSI model. The Internet Society is not responsible for defining standards at this layer. Instead, it supports a number of WAN and LAN technologies defined by other standards authorities such as IEEE and ISO. Some of the more important are shown on screen, but this is far from a complete list. You should also note that any functions of the OSI session and presentation layers need to be built into a TCP/IP application layer protocol if required. The Internet layer is responsible for addressing and routing. It consists of a number of protocols, some of which are shown on screen. Internet Protocol, or IP. Each network interface connected to a TCP/IP network should have a unique logical address which allows packets to be routed to it. An IP address has two parts: a network portion, or the prefix, and a host portion, the suffix. In a network consisting of multiple network segments connected together by routers, the routers need to know how to forward packets to remote destinations. They do this on the basis of information stored in their routing tables, which contains instructions on how to forward packets to remote networks. These networks are identified by their prefixes. The IP addresses of the source and destination hosts are included in the header of an IP packet, the structure of which is shown on the screen, which I've left there for you. Each row represents 32 bits. The packet header is arranged in blocks of 32 bits, which are referred to as words. The options field, if used, is padded out to a multiple of 32 bits if necessary, using null characters. The minimum size of the header is 5 words, i.e. 20 octets. The maximum size of a packet header is 15 words, or 60 octets. In TCP/IP, 8 bits are referred to as an octet rather than a byte. In the early days of development, manufacturers had not standardized what was meant by a byte. 6-bit and 7-bit bytes were still in use. The entire packet, which includes header and data payload, can be up to 65,535 octets in length. However, its actual size may be limited by the maximum size of the frames which carry it across a particular data link. TCP/IP hosts must be able to accept packets of at least 576 octets. This is the default maximum size of packets handled by many applications that use UDP, described later in this section. The IP packet header fields are described in the next table. You will not be examined on these in detail, however you should understand the use of TTL, or time to live, the protocol and the fragmentation fields as described shortly. So we have the header field and the bits. So for example, let's go through them. The VER, or version, is the IP version set to 0100 for IPv4 and 0110 for IPv6. Then we have the H length, or header length, and this is the length of the header in words. And then we move down to type of service, which we'll come back to. I'll describe that after. And then you've got total length, which is the total length of packet in octets. And you've got identification, which is a pseudo-random number set at the start of a host session and incremented by 1 for every packet sent. It is used to identify packet fragments. Underneath that you have fragmentation. So the first bit is always set to 0. The second specifies whether the packet is a fragment. The third, whether there are fragments to follow. The remaining 13 bits specify the fragment offset, i.e. the fragment in the original packet data, which is the start of the fragment's data. Then you have time to live. So each router decrements the TTL by 1. When the TTL is 0, the packet is dropped. The original value depends on the sending application. It is used to prevent packets caught in a routing loop from circulating endlessly between routers and clogging the network. So as each packet traverses a router, it will decrement the TTL by 1. And basically when it gets to 0, the packet is dropped. Moving further on, or the next one down, is protocol. This defines a protocol whose data is being carried in the packet. For example, 6 for TCP/IP, or 17 for UDP, and 1 for ICMP. Moving down, you've got checksum. A 1's complement checksum based on the content of the packet header, used to check that the header has not been corrupted. Then you have the big detail here is the source IP address followed by destination IP address, and then you've got the options and padding, which is to carry optional data such as timestamps. So the type of service is as follows. Basically, the use of 8 bits of the type of service field has been redefined several times in various RFCs. Originally, it was intended to allow applications to request one of 4 different kinds of service for their packets. Would be low delay, high throughput, high reliability, or normal service. Routers would then route packets along paths with those characteristics. However, this depending on intermediate networks being able to provide those services, which often was not the case. Consequently, the default value of 0, or normal service, was often used. Currently, the first 6 of these 8 bits are defined by RFC 2474 as the Differentiated Services Control Point, or DSCP field, which allows an application to request that a router forward certain classes of traffic across appropriate links. These traffic classes include EF, or expedited forwarding, similar to low delay, or AF, assured forwarding, which is similar to high reliability. And then we have default, which is similar to normal service. In other words, DSCP plays a similar role to the earlier TOS field. The last 2 bits are defined by RFC 3168 as the ECN, or Explicit Congestion Notification field. This requires both endpoints and the intervening routers to support the ECN mechanism, which is optional. When a network is congested, packets may be lost. When endpoints detect lost packets, they will reduce the rate at which they send data to each other. With ECN, routers detecting impeding congestion can use the ECN field to send a signal to endpoints, allowing them to reduce the rate at which they send packet data before packets are lost, thereby avoiding the extra overhead of retransmission lost packets. So here's an exam tip. You may still come across references to type of service as well as the current DSP, DSCP or ECN. The information in this section is provided for the sake of clarity. You will not be expected to demonstrate a detailing understanding of it in the exam. However, you should know what type of service DSCP and ECN stand for. Protocol numbers identify internet layer and transport layer protocols. The number in the protocol field specifies the protocol encapsulated by the packet. You should be familiar with those listed on the screen right now. Packet fragmentation and reassembly. A router may receive a packet which it needs to forward across a network link whose maximum frame size is too small to contain the entire packet. In this case, the router divides the packet into a number of fragments which are sent separately across the link. The fragments can be identified as belonging to the original by their identification number. When fragments arrive at the destination host, they can be reassembled in the order using the identification number together with the information in the fragmentation field. Fragments are only reassembled at the destination host, never by intermediate routers. ARP, or Address Resolution Protocol. When a packet is sent across a LAN data link, it needs to be encapsulated in a frame with the destination MAC of the destination host. ARP is used to map the IP address of the destination host to its MAC address. These mappings are then stored in an ARP cache in memory for a period of time, which depends on the operating system and how it has been configured. The default time for Cisco routers is 4 hours, while for most Microsoft systems it is 2 minutes. In this section we also look at a number of other protocols relating to ARP, such as SLARP, or Serial Line Address Resolution Protocol. We'll also look at inverse ARP and RARP, which is Reverse Address Resolution Protocol. You should note that ARP is only used by IPv4, not by IPv6. ARP determines the destination MAC address for each frame by first looking in the ARP cache for an entry matching the destination IP address of the outbound packet. If there is a matching entry, the MAC address is retrieved from the cache. If not, ARP broadcasts an ARP request onto the local subnet, requiring the host with the IP address in question to reply with its MAC address, as shown on screen. Note that the broadcast MAC address is FFFFFFFFFF, and the corresponding broadcasted IP address is 255.255.255.255. The ARP reply from the target host is a unicast, as the query host provides its own MAC address in the original ARP request, and this is added to the target's host cache. Most systems allow the ARP cache to be configured with its static address. This speeds up the process of address mapping and reduces network traffic. However, the ARP cache will have to be updated manually whenever a network card, whose MAC address is represented in the cache, is changed. It will also need to be updated manually whenever an IP address of a target machine is changed. Manual configuration should be avoided wherever possible. If the destination host is not on the same network as the source, the packet must be forwarded to the source host's default gateway. In this case, ARP is used to discover the MAC address corresponding to the IP address of the default gateway. The ARP header. The fields of the ARP header shown on the screen. Each row represents 32 bits. The SHA and the THA are typically the senders and the target MAC addresses. The SPA and the TPA are the senders and the target's IP addresses. The lengths of the hardware address fields shown are those for Ethernet. In the event that another hardware type is used, the lengths of these fields can be specified by the HLEN field. Some common values of the other header fields are shown on the right hand side, as you can see. You've got H-type, P-type and OPA. The usual hardware type is Ethernet and the only protocol type is IPv4. The two most common operations are request and reply. SLARP, or Serial Line Address Resolution Protocol. A host on one end of a serial line learns the IP address of another host at the other. It can also automatically assign itself another address on the same network. As there are only two hosts in the serial network, the self-assigned address will be unique. This is effectively what SLARP is. Let's look at inverse ARP quickly. In a frame relay environment, hosts are connected to neighbouring hosts via virtual circuits and can advertise their IP addresses to their neighbours using an inverse ARP. In this way, a host will be able to associate a neighbour's IP address with a DLCI, also known as Data Link Connection Identifier. So they will associate a neighbour's IP address with a DLCI of the virtual circuit connecting to the neighbour. but we'll cover frame relay and DELCs more in module 13. Let's move on to RARP. This protocol was used for dynamic IP address configuration of hosts. It allowed a host to determine its IP address by broadcasting a RARP request. If there was a RARP server on the network configured with a database mapping IP addresses to MAC addresses, it could assign an IP address to the requesting RARP client based on that client's MAC address. This protocol was superseded by BOOTP, which allowed a BOOTP server to provide the client with other TCP/IP configuration information in addition to its IP address. BOOTP suffered from the same disadvantage as RARP, i.e. the BOOTP servers needed to be configured manually with the MAC and IP addresses of their clients. BOOTP has now been replaced by DHCP, which allocates IP addresses to the MAC addresses of the requesting DHCP clients dynamically from a range of IP addresses called the scope. Moving on, ICMP. So ICMP is a protocol whose function is to help maintain TCP/IP networks and diagnose faults in them. It was first specified in RFC 792 and is considered to be part of the Internet layer. The ICMP header fields are shown on screen. Each row again represents 32 bits. Some common values of the type and the code fields are shown on screen. The content of the rest of the header will vary according to the values in the type and code fields. Note, the DF flag is the second bit in the fragmentation field of an IPv4 packet. If it is set to 1, the packet will not be fragmented. ICMP control messages are encapsulated within IP packets and can be routed throughout a network. ICMP is used to carry out the following functions. So, building and maintain routing tables. So on most host systems, most systems will forward packets addressed to remote networks via a default gateway. The address of this gateway is configured on the host. However, since routers share information about network topology with each other, the default gateway may learn of a better route via another router on the same network as the host. When this is the case, an ICMP redirect message is used to advertise the host of a better route and update the host's routing table accordingly. ICMP can also be used for diagnosing problems. For example, ping. The ping utility is used to send ICMP echo requests to an IP address and wait for an ICMP echo response. It reports on the number of responses received and the time interval between sending the request and receiving the response. It is used basically to test whether a host is reachable. Also, the traceroute utility is used to determine the path taken by packets to reach a remote host. It works by sending a series of packets with increasing TTL values to the target IP address. The first packet is sent with a TTL of 1. The TTL will be decremented to 0 by the first router in the path, which will drop the packet. The router sends an ICMP message back to the sending host, informing it that TTL expired. The next packet is sent with a TTL of 2. This packet will be dropped by the next router in the path, generating another ICMP message, and so on. The sending host gradually builds up a list of routers which have handled the packet. This can be used to identify the path taken by the packets, as well as which router is unable to forward the packets any further. Please note, some implementations of traceroutes, such as Microsoft's traceRT command, send ICMP echo requests encapsulated in packets with increasing TTL fields. These may be blocked by firewalls which deny access to ICMP echo requests. To get round this, Cisco's traceroute does not send ICMP echo requests. Instead, it sends packets containing UDP datagrams addressed to an invalid port address. When these packets arrive at the target, it will respond with ICMP destination port unreachable addresses or messages. which tell the sender that the target has been reached. ICMP is also used to adjust flow control to prevent link or router saturation. So if a host is sending packets to another at a rate that is saturating the routers or the links between them, it may receive an ICMP source quench message asking it to slow down. IGMP, so stands for Internet Group Management Protocol. Unicast packets are packets with the destination IP address of a single host. Earlier, when looking at the ARP process, we saw that PC1 used the IP address 255.255.255.255 when broadcasting its ARP request. This was an example of a broadcast packet picked up by all hosts on the local network. Another type of packet is the multicast packet. This has an IP address which matches a group of hosts based on the type of host. For example, a packet could be sent to all routers. IGMP is responsible for determining whether a host accepts a multicast packet. It does this on the basis of the type of host in question. It is also used by routers to determine how to forward multicast packets. However, the details of this are beyond the scope of this course. The transport layer. The transport layer is responsible for end-to-end communication between hosts on the network. There are two transport layer protocols in the TCP/IP protocol suite. They are TCP and UDP. One of the jobs of the transport layer is to accept data from and deliver data to the appropriate application layer protocol. Both TCP and UDP do this on the basis of port numbers, which are used to identify the application layer protocols in question. Port numbers are covered later in this module. So, TCP. TCP provides a connection-oriented, reliable byte stream service to applications. TCP only provides one-to-one communications, or unicast. Sessions must be established between communicating applications. TCP accepts a byte stream from applications, which it breaks into segments. Reliability is ensured by a system of sequence numbers applied to segments. If the destination host does not acknowledge a segment within a certain timeout period, the segment is retransmitted. If a segment is persistently unacknowledged, TCP will close the session and inform the application that the connection has failed. Error control is also provided by checksums, calculated from the contents of each segment. In the sections following, we describe each of these features in more detail. Segmentation. For outgoing data, TCP accepts a continuous stream of bytes from an application layer protocol and divides it into TCP segments, which are sent to the internet layer, where they are encapsulated into packets. For incoming data, the process is reversed, as shown on the screen. The size of the segments, which is configurable on most systems, is typically chosen to be 1460 bytes. This takes into account the MTU, or Maximum Transmission Unit, or largest size of frame payload, of 1500 bytes for Ethernet, and the fact that the sizes of the packet and segment headers are usually 20 bytes each. The structure of the TCP segment is shown on screen now. Each row, again, represents 32 bits. So, source port is the port number of the source application. Then we have destination port, which is the port number of the destination application. Sequence number, which is effectively a pseudo-random number chosen for each connection, incremented by the number of bytes sent. Then you have acknowledgement number, which is the value of the next sequence number expected from the other host. Then we have some offset, data offset, which is the length of the header in words. Control bits. The first 3 bits are used to implement ECN or explicit congestion notification. The following 6 1-bit flags describe the contents of the segment. So bit 0 is urgent, bit 1 is acknowledgement, bit 2 is push, bit 3 is reset, bit 4 is synchronize, and bit 5 is final. You have window, which is window size, used to control the amount of data that can be sent without immediate acknowledgement. Then we have the checksum below, which is based on the contents of some fields from the encapsulated IP packet header and the total length of the segment in octets. Then we have the urgent and options. Urgent is the pointer to the first octet of the urgent data if the urgent flag is set, and options such as the timestamp. Multiplexing, demultiplexing. For outgoing data, TCP takes data from different applications and generates segments which it sends to the internet layer. For incoming segments, their data must be directed to the appropriate application. Applications are identified by their port numbers, as shown on screen. Port numbers are used to specify which applications receive the contents of the TCP segments, or UDP datagrams, from the transport layer. They can take values from the range of 1 to 65,535. Port numbers in the range of 1 to 1023 are well-known port numbers. They are assigned to standard server applications such as telnet and HTTP. And these are assigned by the company IANA. Vendors may also reserve port numbers as registered ports for vendor-specific applications. These are in the range between 1024 to 49,151. Ports in the range of 49,152 right up to 65,535 can be assigned as dynamic or private ports for temporary use by client applications. The server port number needs to be known by clients needing to establish a connection to it. The client notifies the server of its dynamic port number when the connection is being established. Dynamic ports can also be assigned in the range ports immediately above the 1023. These assignments could clash with registered ports. However, it is unlikely that a server application responding to a client request from a workstation with a source port address, for example 1025 say, would confuse that with a server application with the same port number running on the same workstation. Nevertheless, it is better to avoid any possible confusion by using the recommended dynamic ports for client applications. Microsoft, with the release of Windows Server 2008 and Windows Vista, moved from using dynamic ports in the range of 1025 to 5000 to using ports in the range of 49,152 up to 65,536 for client applications, as recommended by IANA. As you can see there, I've listed what I've basically explained. You've got the well-known port numbers were 1 to 1023. The vendor-specific port numbers range from 1024 up to 49,151, and then you've got the dynamic port numbers, which are generally what you'll find a client application connecting to a server. For example, if you look at the server logs and your laptop is connecting to a web server, it will see a source port number somewhere between 49,000 up to 65,535. TCP sockets. The port number is one of the 3 pieces of information required to specify a unique endpoint on the network, which is known as a socket. A socket comprises of the following information: IP address, transport layer used by the endpoint application, and port number of the endpoint application. The IP address specifies the host running the application, and the port number specifies the application itself. The transport layer protocol is also required because some applications can use either TCP or UDP depending on the circumstances. The following table is a list of well-known port numbers which you should be familiar with for the exam. It includes transport layer protocols used by the common applications. So for example, it'd be handy to know DNS uses TCP or UDP 53, SMTP is port 25 TCP, another popular one is IMAP and HTTP. So I would study those and commit those to memory. TCP ensures reliable connections by requiring that each segment sent is acknowledged. If a segment is not acknowledged within a certain timeout period, it will be retransmitted. Segments may be retransmitted until a further timeout period is exceeded, at which point the connection will be terminated. The initial timeout is usually about 3 seconds. However, the timeouts are calculated dynamically based on measured response times. At the beginning of a connection, each side independently sets the sequence number of its first segment to a pseudo-random number. The next segment sent will have its sequence number incremented by 1. Subsequent segments will have their sequence numbers incremented by the number of bytes sent in the previous segment. So if host B sends a segment to acknowledge a segment received from host A, the segment will have its ACK flag set to 1 and will carry an acknowledgement number. This is set to the value of the next sequence number that host B expects to receive from host A. On the screen you can see that part of a TCP exchange after the connection has been set up. Setting up the connection is covered later in this section. So host A sends a segment with a sequence number of 501, carrying 96 bytes of data. The segment is not acknowledging any previously received segment, so its ACK flag is set to 0. Host B sends a segment with a sequence number of 75, carrying 64 bytes of data. This segment also carries an acknowledgement number for the segment just received from host A. Its ACK flag is set to 1 and the acknowledgement number is set to 501 plus 96, which is 597, the next sequence number that host B expects to receive from host A. Host A then sends a segment with the sequence number 597 carrying 256 bytes of data. This segment also carries an acknowledgement number for the segment just received from host B. Its ACK flag is set to 1 and the acknowledgement number is set to 75 plus 64, which is equal to 139, the next sequence number that host A expects to receive from host B. If the sequence number needs to be incremented beyond 429496725, which is a massive number, counting continues from 0. The other mechanism that TCP uses to ensure reliable connections is retransmitting segments. On the screen you can see what happens when host A does not receive an acknowledgement for the segment with sequence number 501. As soon as the segment is sent, a timer associated with that segment is started. Once a timer reaches a value of the timeout period, the same segment is resent. The acknowledgement might not be received for a number of reasons. Typically, these include loss of the sent segment or acknowledgement due to network failure or network congestion, as well as the inability of the receiving host to process arriving packets. In the latter case, TCP will attempt to reduce the number of segments sent at any time across the connection. Eventually, if no acknowledgements are received, the connection will be terminated. So we're moving on to flow control and using sliding windows. So I've put the screen up on to describe, and I'll explain it now. So on the screen you'll see that host A did not send its second segment until host B had acknowledged the first. Having to acknowledge each segment before the next can be an inefficient way of transferring data. TCP handles this by allowing some segments to be sent without immediate acknowledgement. The window size specifies a number of bytes which can be sent without immediate acknowledgement. The initial value of the window size is usually a configurable parameter. However, TCP can modify the window size dynamically in response to changing conditions, particularly the ability of hosts to handle the volume of traffic they receive. As you can see, host A has a window of 1500 bytes and it has 4 segments to send. It can send the first 3 segments without waiting for acknowledgement because they have a total size of 1280 bytes, which fits in within the 1500 byte window. The 4th segment cannot be sent until the first segment at least has been acknowledged. In this example, the first segment is acknowledged. If host B receives the first 3 segments in rapid succession, it might simply acknowledge the third. This reduces the number of acknowledgements that need to be sent. It will only acknowledge the 3rd segment if it has received the previous 2. A receiving host can request the sender to increase or decrease the size of its window by setting the value of its window field. This is useful when a host cannot process all the traffic that it is receiving. Note, TCP is sometimes referred to as an error-free protocol. This means that data will be sent without error, or if the transmission errors occur, which the protocol cannot correct, the connection will be terminated and the application notified of the fact. Applications can be sure of whether the data has been sent correctly or not sent at all. So, establishing a TCP connection. TCP is a connection-oriented protocol, i.e., an end-to-end connection needs to be established between applications before they can exchange data. The connection establishment process is on the screen right now. An application on host A attempts to initiate connection to an application on host B. It sends a segment with the SYN flag set to 1. If host B is willing to accept the connection, it sends back a segment containing an acknowledgement and with the SYN flag set to 1 also. Note that the acknowledgement number is 1 greater than the received sequence number because host A will increase the sequence number in the next segment by 1, even if no data has been sent. Host A sends a segment which acknowledges host B's synchronization segment and contains the first data sent to host B. This process is sometimes known as a 3-way handshake. Terminating a TCP connection. A TCP connection is terminated by a 4-way process as shown on screen. When an application on host A is ready to terminate connection, it sends a segment which contains any remaining data and which has the FIN flag set to 1. Host B immediately acknowledges this segment. It then sends 1 or more segments containing any outstanding data from its application. The last of these will have the FIN flag set to 1. When host A acknowledges host B's final segment, the connection is terminated. User Datagram Protocol, or UDP. UDP provides a connectionless, unreliable transport service, i.e., it neither guarantees delivery of UDP datagrams nor informs applications if it fails to deliver datagrams. Applications using UDP must supply their own mechanisms to ensure reliable delivery if this is required. Applications must construct the datagrams to send the UDP layer below, as performs no segmentation of data streams. The structure of a UDP datagram is shown on screen now. Each row represents 32 bits. UDP header fields are described on screen now. UDP is used for one-to-many communications, i.e. broadcasts and multicasts, where connections are not established. As UDP is a much simpler protocol than TCP, it usually consumes fewer system resources. Note, a datagram is also a generic term for data units which are transmitted unreliably. IP packets are also often referred to as datagrams. There are many application layer protocols. We shall briefly discuss those that are most relevant to the configuration of Cisco routers. So we have telnet, which is a network terminal emulation utility. The telnet provides text-based terminal access to a host running telnet server software. The telnet utility is widely used to perform remote management. Telnet uses TCP as its underlying transport layer protocol. Cisco routers can act as telnet servers and telnet clients. Telnet suffers from the disadvantage that all data is sent unencrypted over the network. This includes the passwords used to access routers, for example. Then we have SSH. Many Cisco routers and switches also support SSH, which offers more secure text-based terminal emulation using public key encryption to authenticate remote logins. TFTP. It is used to copy files between a TFTP server and a TFTP client. It does not support encryption or authentication, though some implementations of TFTP software might require authentication. It is a quick, convenient, but not very secure way of downloading files to a router or switch, particularly operating system images and configuration files. TFTP uses UDP rather than TCP as the underlying transport layer protocol. DHCP. So workstations can obtain their IP configurations, so for example IP address, subnet mask, default gateway, etc. from a DHCP server. A DHCP server maintains a range of IP addresses and corresponding subnet masks which can offer to DHCP clients. In addition, it can provide other IP configuration information such as default gateway and DNS server addresses. When a DHCP client boots up, it broadcasts a DHCP request to the LAN. One or more DHCP servers will respond with offers of configuration information. The DHCP client will usually accept the first offer it receives. When it does, the DHCP server assigns the offered IP address to the DHCP client's MAC address, preventing that IP address from being offered to any other DHCP client. The IP address is offered for a specific lease time, which is configured on the DHCP server. After the lease expires, the DHCP client must obtain a new lease. DHCP clients will periodically attempt to renew their leases before they expire. Later in this course, you will learn how to set up a router as a DHCP server. DNS. DNS servers resolve domain names to corresponding IP addresses and vice versa when requested by DNS client software known as the resolver. By default, Cisco routers are configured to query DNS servers by broadcast in order to resolve domain names to IP addresses.